So now if we have two poles, second order system, take the same case, AS equal to A over 1 plus S over omega P1 into 1 plus. Now instead of a single pole, I have two poles. Correct? So what would happen? Let's say I am again plotting this loop gain. So you can assume any, you can assume that omega P1, omega P2 are at the same frequency, or you can assume that omega P2 is at higher frequency compared to omega P1. It does not matter actually. The shape of the Bode plot will just change, that's it. So if this is omega P1, minus 20 dB per decade, correct. Now if let us say my second pole hits here, so how will this shape change? It will start decaying with minus 40 dB. Okay, if omega P1 and omega P2 were at the same frequency, then you should have started with minus 40 dB per decade right from here, very first point. Okay. Now let us say this is your unity gain somewhere here. This is your unity gain. Now do the phase plot. So again starting from (180 degree), it's a negative feedback. So what will be the phase here? So if let us say this is 10 times low and 10 times higher, so your phase will start dropping from here. So this will be 135, correct. And let us say this is more than 1 decade apart, so it will remain 90 degree, and then the effect of second pole will start coming 1 decade before this. So this is 90. What will be the phase here at second pole? 45. And what is the phase here? 0. So now look at the gain. You are hitting 1 at higher frequency, but your phase has already crossed 0 degree, which means this is your unstable, because phase margin is 0 here at loop gain greater than 1. As long as this 0 phase happens before your omega UGB your system is unstable. Correct. So, phase margin here is 0. If this 0 would have happened after beyond omega UGB, then you could have achieved some phase margin, and that is what you try to do, which means your second order system has a tendency to become unstable. So, now let us assume this. Let us take another case. Let us say your omega P2 is at omega UGB, then what would happen? Unstable? How come unstable? 45 degree, yeah. So, your phase margin is 45 degree. And in order to have a very good system, good stable system, what is the phase margin required? This is marginally stable actually. This is a practical requirement, not theoretically. You can say your system is stable even if your phase margin is more than 0 degree, even 10 degree system is not unstable, because it will not keep oscillating, or because it will die out, but it will have lot of ringing and it will take very long time to settle. Okay. So, practically this is the requirement, that in order when you are designing a system, a good stable system will always have a phase margin of around 60 degrees or higher. So, 45 degree is a very badly designed system, okay, even though it is a stable. So, practically we consider it as an unstable system below 45 degree, even though theoretically it is not. That is why never design a system which has a phase margin 45 degree or below. Make sure it has, even if you design with a 55 degree or so, still that is okay. So, sometimes when you design a system, your phase margin may vary across the corners. So, at the worst corner, if you have a 55 degree or so, then it is acceptable, but never hit 45 degrees also, it will have lot of ringings, which means even if you place your second pole at a UGB, the maximum phase margin you can get is 45 degrees, which is not good. Okay. So, practically it is not good. We cannot call it a good stable system. So, your second pole should always be outside your UGB. Second pole should always be outside omega UGB, and that is what we do when we say compensation. We try to push the second pole outside your UGB. So, this is the thumb rule. You cannot have a two or more than two poles within your UGB. So, whenever you are designing your system, make sure have only one pole, and the second pole should be outside your bandwidth, unity gain bandwidth. In order to achieve that, so there are different types of, one thing as, okay, you can reduce the pole frequency of the first pole, so that the second pole will automatically. So, here if I reduce the frequency of my first pole, then my UGB will also shift inside and your second pole will automatically go outside. So, reduce your bandwidth. So, your omega P2 is not changing. So, just reduce your bandwidth so that it will become outside. So, that is a one type of compensation. Other, you can place a 0 and cancel that second pole. So, both pole 0 cancellation and dominant pole compensation, two main techniques are used. So, we'll look into the closed loop response of this second order system, and we'll relate this loop gain parameters, which are your basically phase margin, and that's the main motive to analyze the loop gain, because we want to find the phase margin. And so we will try to relate the closed loop system with the open loop and see what is the relationship between your damping factor and phase margin. Okay. Second order so let's draw your standard closed loop diagram with beta factor. Connected in negative feedback. So for second order system, A should be A naught over 1 plus S over omega P1 into 1 plus S over omega P2. Okay. And we know that V out by V in is A over 1 plus AS beta, correct? So, we will substitute this A naught over 1 plus S over omega P1 into 1 plus S over omega P2 1 plus A naught beta over and we will just try to solve this. So, what you get A naught over okay. So, we will break the, so just multiply two terms here and we will see what happens. So, what you get here S over omega P1 plus okay plus which could be written as plus and we know what is the transfer function for second order system, standard transfer function. Plus omega n square, and if there is any gain we can write k. Okay. So, here k is a naught over 1 plus a naught beta, and this we know that if you do not have any pole, so that's so put s, substitute s equal to 0, you should get that a naught over 1 plus a naught beta, and rest of the term is coming because of the poles. So, what is zeta? What is omega n square? Square root of 1 plus a naught beta omega p1 omega p2, which implies omega n equal to square root of and zeta. So, this is S. So, 2 zeta omega n is omega p1 plus omega p2, correct. So, from here we can calculate zeta. Zeta is half of 1 over 2 n 1 over omega p1 plus omega p2 divided by 1 plus a naught beta okay. So, let us move the constant terms outside. So, you get twice of square root 1 plus a naught beta, and we will have another term here inside. So, I will move this omega p1 and omega plus omega p2, the numerator inside the square root. So, it will become square. So, omega p1 square plus omega p2 square plus twice of omega p1 omega p2 divided by okay. Okay.